Um,
Yeah.
So this stems from, as I was saying, this talk of a researcher about non-classical negations, which I didn't attend. So it would be very nice to me to know which was the background of, or which is the background of the people here present on formal logic, like who has a course on formal logic or who did some exercises with the P's and the Q's and and the trees of, of decision and the truth tables and so on, or who has worked in logic here? Like, what's the background?
Let
I
me
barely have a
a little
background.
Gabriela and Olga?
I did it.
What?
I did it.
Oh, nice. Olga?
there is a poll now you can vote.
Oh, yeah. That's nice. Yeah, I think I'm mild actually. I have just a course in like two courses like a long ago.
Okay, now we got the
Okay. Yeah. So um very shortly and only to start from Aristotelic logic, which worked with propositions, we came down to mathematical logic, thanks to the work principle mainly of Gottlob Frege and George Boole, which is abandon the relationship between logic and human reasoning. Like, we don't care anymore about if humans do this or what's in the mind of the reasoner. We only care about the validity of the deduction from symbolic relationships, which are empty. The meaning which we imposes over the symbols is not part of the discipline, so that's why it's formal. So we have these connectives like negation and conjunction, disjunction, exclusive disjunction, material conditional, material equivalence. Some of you have background in programming, like Gabriel, Flor. Of course, Thomas has, but uh, anyone else? Any language?
Just a bit, yeah, but not profound.
Thank you. So the thing is that this is very much like logic gates and legal gates, and we use a bit of this. Thank you, Flor, in programming, so we'll be very familiar onwards. This might be much arcane, like the quantifiers, the universal, which reads like for every x there is a property, and existential, that there is some x which has that property, like um, for every x y alguna any property of x or existential sum. So that's all the basic things we need to do first order logic. How can I erase this? So this, we have this truth table, like if you have p, which means whatever you want, like a cat's on the table, the negation makes that not a cat is on the table will be false. If a cat on the table, it's true. But if a cat on the table is false, not a cat is on the table is true. Notice that I didn't say a cat's not on the table because the negation works like a bit different, like in natural language. The conjunction is like Thomas has a cat and today is sunny. If both are true, the conjunction is true, but in any other case, it's false. The conditional is more tricky because if the premise is false, the conditional is always true. So if a dragon is in my table, Thomas is bald, has no hair in his head. The condition will be true, regardless both are falses. So the thing is that this raises some problems in interpretation, and this has been used to explore and develop logical systems which do not accept this material conditional. But in the classic logic, we have this as an axiom, so we accept this truth table and everything which follows, which may be very odd. The biconditional is if and only if, so we need that both of these are true, both of these are false. Disjunction is one or the other, but if both are true, it's okay. But the exclusive disjunction is more strict. If a cat is on the table, it's true, and I have 5 fingers, true, the exclusive disjunction will be false, which is very useful because we can do things that we cannot do with this disjunction. So the thing is that there are some laws we have to obey in here, which are axiomatic. That is what changes when we change from a classical negation, which is this, to quantum negation or relevantist negation or so on. We can reject identity, but this will be very messy. We can reject excluded middle, which means that we cannot accept something which is in between true or false. For example, we have a cat is on the table, and or it's not the case that a cat is on the table, and we shouldn't accept that a cat is on the table and a cat's not on the table, which means we don't accept contradiction, or we cannot accept that a cat is on the table, or there is not the case that a cat is on the table, which have any middle value, like 0.5 true, for example. This is both of laws are more tricky. No, this is very, very easy. Like conjunction is commutative. Doesn't matter which goes first. And the Morgan is that the negation of disjunction is equivalent to the negation of both parameters as a conjunction, and the negation of a conjunction is equivalent of the negation of both parameters as a disjunction. We can see examples, but so far everything. The only thing I need you to have from this is that this is an axiomatical system, which give us some rules of what we're not allowed to do. We're not allowed to accept true contradictions. For example, I have a cell phone and I don't have a cell phone. We don't accept that like as a true statement. We will see that some logic, like the paraconsistent and dialectic logics, do accept this. So classically, we stick to this. And we can use this to formalize natural language statements, to redact or eliminate semantic ambiguity, to guarantee validity of deductions. We can formalize scientific theories, mathematical proofs, natural phenomena, and we can do programming. So, for example, this is the thing is, this is formal, so we can make absurd statements like P can be whatever we want. Like, for example, Donald Trump is, I don't know, a type of ice cream. And we can say that the King of France is bald. Not any of those is true, but we can take them as whatever, and we can see the truth table, and if we assign a truth value of any of those, we can see what follows. So we can clarify statements like, for example, not the same to say, I do not have a cat and a dog, and I don't have a cat, and I don't have a dog. Because here, it requires that if I have, for example, a cat, this might be false, but this might be true. But if I have a cat, this is false still because I require not to have a cat, not to have a dog. So I need to to meet both conditions. Here I don't. Only one is enough to this to be true. So natural language is ambiguous. Formal language is very precise in the sense that have only one meaning. That's one use of formal logic. But sometimes we don't want this type of restriction. We want less restriction or more restriction. For the example, with the material conditional, which anything is false as a premise will yield a true deduction of if this, then that. If we don't want that, we might restrict even more. So add more laws to avoid that. We can formalize science. This is an example which is very curious, where in order to make science like Newtonian gravity without numbers, we get something like that in order to express a derivative. This is very cumbersome. No one will work with this, but it's possible. We can. This book of Hartfield is Science Without Numbers. He make himself the work. He did himself the work to translate everything we need to know about Newtonian gravitational theory into formal language without any number. Only these quantifiers, properties, and operators like conjunctions here. But this is like for the sake of being annoying. Like Hartfield doesn't do anything practical with that. Nevertheless, what is mass, which changed from a Newtonian context and it's a different concept in a Einsteinian framework. Like if we accept relativity, the concept of mass changed a lot. But mass is actually very ambiguous in natural language. Even in science, it's a bit of ambiguous. So here, Hermes in the 60s make a formalization of what mass means in this context, which for time I won't read it, and make it very precise and avoid any paradox or confusions which arise in the natural language when we talk about that scientific theory. So we can also formalize scientific proofs. This is from the Principia Mathematica of Russell and Whitehead, which is, they took like 55 theorems to to deduct, to prove deductively that 1 plus 1 is 2 in, I think this is after group theory. So probably this is addition in any group, more general than addition in the set modulo n. I think this is just the most general addition, but the thing is that they took a lot of logic to prove that, which is very curious. They tried to reduce each mathematical statement to logic, like to ground all mathematics in logic, but they failed due to the Gödelian incompleteness theorem and the Zermelo-Fraenkel choice model of seed theory. So this program like is dead now. It is dead from a century ago, but was very interesting the attempt and how hard it is. Like you think like 1 plus 1 is 2 is very easy to prove. This is very dear to me. This is a seminal paper which model neurons as logical gates. So you can model natural phenomena. For example, here, a presynaptic neuron is in the time t minus 1 is activating a neuron in time 2, which is a biconditional. Here, two presynaptic neurons, one or the other, if they fire in time t minus 1, this junction is activating the third one. So here, two neurons, we need both of them. It's a conjunction. This dot is replacing the conjunction to activate this neuron at time t. And here one is inhibiting the neuron and this is activating. So we need that the neuron 1 is true or activated, and not the neuron 2, because this is inhibiting the third one. So you can formalize all the synaptic relations, possible relations with formal logic, and treat neurons as computers in the way our logic gates we have before in vacuum tubes or transistors. And actually, when you program, you can use logical connectives to do stuff. So basically, the thing is, this is the classical framework. This is the received view, but we get this. Like, if we violate some rules of, I said before, this is unary gates. This is the negation is a unary gate. We have an input 0 or 1, true or false, and you get the author number. Like 0, you get 1, 1, you get 0. But this is the Pauli X gate, which is all of this. You can see it as negation because are unary, not binary. You get one input, you get one output, but this is very classic. The Pauli X, Pauli Y use imaginary numbers. Pauli Z use negative numbers. Handmark negation is like, I don't know what it does in this matrix. Phase negation use imaginary and 1 and 0. P, no, this is just this E to the I to the P divided by 4 is very familiar from things like Fourier transforms and a lot of things, but it's here for reasons which I don't know. This is our two like binary operators, which has more complex matrix and so on. And the thing of all of these ones is that they violate some actions. For example, the excluded middle, we have to accept values which are not true or false, not 1 or 0. And that make that we, if want to model things which include this relationship which are very messy or strange, we have to go beyond classical axioms and say no to some of them and say yes to new axioms. And that is one of the possible contexts of a non-classical negation. Like, we try to say no to something, like if not the case, like if I don't have a cat, it's true that I have a cat. May not be straightforward for quantum context. They might be many values in between, or they might be some relationships which have no semantical equivalent. So we try other axioms, polyvalent, 3 values instead of 2, 4 values, some things which are false, neither false nor true, or false and true at the same time, like 0 and 1, or not 0 and not 1. So what we gain with this is that we can express, predict, and explain a lot of things which goes beyond the more standard ways of deduction or reasoning. So that's what I can very rapidly summarize about non-classical logics. They emerge like fuzzy logic, the one of the washing machines, infinitary, intuitionistic, many-valued, per-consistent, quantum, relevance, adaptive, free. They emerge to work with things which might benefit from deduction, logical deduction, but they don't behave as yes or no, 1 or 0. Para-consistent, for example, is used in law or in philosophy a lot. Fuzzy in washing machines or control systems, which you avoid using derivatives, making logical programming, so you don't have to numerically integrate or something. And quantum try to formalize very weird quantum things, and in quantum computing may be useful. And relevance try to be more restrictive to only accept conclusions which make sense. Like, as I say in the example, like forbidding the if then, the conditional classical implicances, which are very odd. If something is false as a premise, everything which follows is true. That shouldn't be very useful to use to implement in human reasoning at least. So if you are interested in this, you can download this book. I have a couple of books more. I can send it to you if you like, but that's what I can talk to you now about formal logics and non-classical formal logic. Thank you for listening. Questions and criticism and comments. Everything will be much appreciated.